Hello, everybody. So far we've defined Turing machines and discussed some of its basic properties, the robustness of Turing machines to particular definitions, uh, this notion of recognizing versus deciding, the ability to simulate a Turing machine with a universal Turing machine, the ability to encode Turing machines and to ask questions about Turing machines. We've seen some beginnings of our understanding of Turing machines, and what we'll continue now with is by starting to discuss what Turing machines cannot do. Just like we did for DFAs, we showed what cannot be done by a DFA through the pumping lemma and through mile narrowed. Here too, we'll show what cannot be recognized, cannot be decided. Um, Indeed, I think that we have more intuitions about things that can be done than things that cannot be done. This is kind of the algorithmic versus complexity aspect of things. But when we don't talk about efficiency, in fact, it is possible to show that things cannot be computed, and it's not necessarily extremely hard. So this is what we're going to develop in the next few videos. And we'll start with a very simple argument about the existence of non-recognizable languages through a counting argument. So assuming the Church-Turing thesis, this means that there are problems that no computing device can solve, and even in the weaker sense of recognizing, not even deciding. And we can use it through a counting argument. We will show that there is no onto function from the set of all Turing machines to the set of all languages, even over 0, 1, definitely over any finite sigma. But 0, 1 is sufficient to show this impossibility. And so what does it mean that there is no onto function, or why is it contradicting anything? Because if we look at the function that for every Turing machine associates, maps it to the language it recognizes, this is a function. And if all languages would be recognizable, then this function would be onto, because for every language there will be some Turing machine that it's mapped to it. So every mapping from Turing machines to languages fails to cover all possible languages. In particular, the mapping that maps a Turing machine to the language it recognizes fails to cover all possible languages, and therefore there are languages that are not recognizable. So there are more problems to solve than there are programs to solve them. If these are the languages over 0, 1, and these are the Turing machines, this is a smaller set. And here we mean that it's smaller, we mean it in the sense of infinite sets. So if we try to create a mapping from Turing machines to languages, it won't be onto. There will be many languages that are not covered. So what is this idea of onto? F from A to B is not onto if there exists some B in B, such that for every A in A, the mapping that takes F, the mapping F applied to A doesn't give you B. So there is a B that nothing mapped to it. No A is mapped to it. Let L be any set, and 2 to the L is the power set of L, Right? The power set is the set of all subsets of L. There is a theorem that there is no onto function from L to 2 to the L. 2 to the L is larger than L. And the proof, we can prove it in more than one way, but for example, by contradiction, if we assume that there is a function that is onto from L to 2 to the L, let's define the set S, which is all the x's in L, such that x is not in f of x. So for every x, there is a set f of x. And so there, and given a set and an element, we can ask whether an element is in the set. So we can ask, it's legitimate to ask if x is in f of x. And we want to define a set that contains all the x's that are not in f of x. This is a set, and it is a set over elements in L. So in itself, this is a set, sorry. In itself, this is a set, this is a member of 2 to the L, right? It is in the power set of L because it is a subset of L. Now, if F is onto, then there is some element in L that is mapped to S. So there is some y in L such that f of y is S. And now we will ask ourselves whether y is in S or not. And this will create a contradiction because the two only options are impossible. Suppose y is in S. So by the definition of S, y is not in f of y. Suppose y is in S, by the definition of S, y is not in f of y, which is S. So we got to the conclusion that y cannot be in S. Why does it mean that if y is in S, then y is not in f of y? This is how we define S. S is all the elements that are not, all the x's that x is not in f of x. So let's assume the only other possible thing. Let's suppose that y is not in S. Then by the definition of S, y is in f of y. Because whenever, for every y that is not in f of y, then y is in S. And so these are the only two options. Y can be in S or not in S, and therefore we reach a contradiction. So this is a proof by contradiction. I'll give you another proof, which is not by contradiction, kind of a direct proof, and you can choose which one of them you like. It's the same proof, it's just phrasing it a little bit different. So let's f be any function from L to the L, but we want to prove that f is not onto. So we won't reach a contradiction, but we will prove that it is not onto, and since any function f will not be onto, it means that there is no onto function. And the proof is very similar. So given f, we're going to define S just as before, all the x's in L such that x is not in f of x. And for every x in L, so this is the different, what do we know? If x is in S, then x is not in f of x, by the definition of S. And if x is not in S, then x is in f of x. So in either way, we get that f of x doesn't equal S. So what did we show? We showed that for any function f, when we define S given this function f, we get that no x is mapped to S. So this means that f cannot be onto, because we found a set S that nothing is mapped to it. So what does this mean for us? There is no function from L to 2 to the L can cover all the elements of 2 to the L. And this is no matter what the set L is. The power of set 2 to the L is always strictly larger. And again, because we are not thinking on finite sets, it has larger cardinality. This is right. How we talk about the size of infinite sets. We talk about their cardinality. So the theorem is that there are non-recognizable languages. So suppose that all languages are recognizable. Then for all languages L, there is a machine M that recognizes L. So now this means that there is an onto mapping from Turing machines to languages. The mapping is the one I mentioned before. For every Turing machine, I map it to the language it recognizes. And we said that every language is recognizable, therefore, this mapping is onto. Let's look at Turing machines. Turing machines can be encoded. So they are a subset of 0, 1 star. And so if we think about the encoding of a Turing machine, it is a string, and therefore Turing machines are encoded in 0, 1 star. So this is the set M. Languages over 0, 1, what are those? These are a set of strings. So a language is the set of words in the language, and each word is a string. So for every subset of 0, 1 star, we have a language. So this is 2 to the M. So the Turing machines are contained in M, and the languages are 2 to the M, and so there is no onto function from M to 2 to the M, and therefore there is definitely no onto function from Turing machines to 2 to the M, so from Turing machines to languages, and this is a contradiction. I want to very briefly say that this idea comes up in other contexts earlier even, and I want to mention Russell's paradox in set theory, right? And which is highly related to this notion that there is no onto function from sets to their power set. So in the early 1900s, there was a movement by logicians to define a consistent foundation of mathematics, a logical system that is consistent and somehow based on some basic axioms and basic derivation, we can derive everything that's true in math. We will come back to this idea and towards the end of this chapter. But let me mention kind of one of the first kind of issues with this idea. And that's through this difficulty of defining a consistent way of viewing sets. So suppose X is the universe of all possible sets. Frege's axiom tells us, or gives us a way of defining sets. It says essentially that for every property, F, we can define a set. So for every property and over every universe, which we can think about as a function, F, from the universe to 0, 1, a Boolean function, we can define a set, which is all the elements in X that satisfy this property. So this means that, we can define this set S in X such that f of S is 1. Properties give you, predicates gives you a way to define sets. And so this is Frege's axiom, and And we can define now the set F, which is all the sets S in X, so that S is not in S, right? Since being in S, right, is a property, we can define a set based on this property. So if you think about this function f that over this domain X of all possible sets, which is 1 if S is not in S. So then we get by Frege axiom another set F. And now we will reach a contradiction like we did before. Suppose F is in F, then by definition F is not in F. And so if F is not in F, then by definition F is in F. And this is a contradiction. So this logical system is inconsistent. This kind of naive way of defining what is the set universe of all possible sets and how can sets be defined reaches a contradiction, reaches a paradox. And yeah, so this logical system is inconsistent, and we will discuss this issue of logical systems and can they be consistent and what's the price to pay. So as parting thought, some problems are not recognizable regardless of efficiency. It's not an issue of efficiency at all, but who cares, right? There are so many problems. We know that some problems exist, but perhaps we can't even define them. We cannot even understand them. So who cares that they cannot be computed? By itself, it's not such a devastating blow. It could be that everything that we really want to compute is actually computable. So this we'll see in the next video. Thank you.